By the way, just so you know, just for you guys, my AP students, I got online and I found loaded dice. You can find anything online, right? I wouldn't recommend gambling with them. I think you might get shot if you use them, but, or at least maybe stabbed. I was pleased to see that they came from Mountain Home. Conditions. So we're comparing two means, so we're going to be comparing two groups. Conditions are pretty much what we're used to, SRS. We have two SRSs from two distinct populations. And normality. Both populations are normally distributed. However, in practice, it is enough if both distributions have similar shapes. So we're talking means here. The central limit theorem would apply, but let's say we have two separate SRSs, two separate samples, and we're going to compare the two, but both of them are less than 30. Let's say one's 27 and one's 20. And we take that data and we put it into our calculator and we graph both curves, say both histograms. If both histograms have a similar shape, then you can say that we're approximately normal. So if you have a left skew for both, you're good. Move on with your calculations. Okay, as long as they're both similarly shaped, we're good. Independence. Both are independent and one does not influence the other. One does not influence the other. Those are the three main ones, but in addition to that, the population has to be at least 10 times larger than the sample. That's sort of one we probably don't talk enough about until we get into proportions, but it's something that's important all the time. So what do we have? So we've got population, variable, mean, standard deviation, sample size mean again, and standard deviation again. So we have two populations. The first population, the variable would be x1. The mean would be mu sub 1. The standard deviation, sigma sub 1. And you don't have to use ones here. You can use other letters or whatever, but the idea is the same. N1 for sample size. This mean would be x bar 1. And this standard deviation, S1. For population 2, well, it's all that. It's just 2's. These two guys here are our parameters. So they're the population mean and the population standard deviation. Over here we have our statistics, our sample mean and our sample standard deviation. Now, we've done a lot of standardizing at this point. This is no different. This is going to give us a two-sample, not this, but the next thing I'm going to show you, a two-sample z statistic. Why z? Because we have normality. So z equals, put it on my chair. I won't miss it on my chair. Anywhere else and it could get lost. Thank you. Z equals the difference of x bar 1 minus x bar 2 minus the difference in the population means, mu sub 1 minus mu sub 2. So x bar minus mu, with the differences in them, divided by the square root of sigma 1 squared over n sub 1 plus sigma 2 squared over n sub 2. So it's the two sample, it's the difference, it's the change in them. Any questions at this point? First period asked all the good questions. Where are your questions? You know what first period questions were? And this might tell you a little bit about my first period. Is there a way to do that in the calculator? Yes, there is. Take your calculators out, turn them on. I want you to see if you can find it. Press Stat, go over to Tests, and see if you see something that looks like it might do this. Did you find one, Paige? I don't know, I'm not looking myself. What does it say? That would be correct. It is the 2-samp z-test. This isn't the world's worst formula by any stretch, but the 2-samp z-test is pretty handy for cutting us short on some time, or cutting some time out of it. Okay, so that's if we know sigma. What if we don't know sigma? It's T, you're right, you're right. So is everybody with me? Okay. So we have the two-sample T statistic. This is where sigma is unknown. So we've got to calculate the sample standard deviation. So that gives us T. Conditions are all the same except normality. We don't really need it. X bar 1 minus X bar 2 minus mu sub 1 minus mu sub 2 square root S sub 1 squared over N sub 1 plus S sub 2 squared over N sub 2. And what's the question you might have on your head? Yeah, can you do it in the calculator? Well, yeah, of course you can, but is there a shortcut? Yes, there is. It's the two-samp T test. Two-sample T test. And there's one more formula I'm going to hit you with today. The confidence interval for a two-samp T statistic. X bar 1 minus X bar 2 plus or minus T star times the square root of S1 squared divided by N1 plus S2 squared divided by N2. Confidence interval. Is there an interval test for this? Any luck? Did you find it? What's it look like? What do you think?
T-test?
Not the t-test. You've got two samples in this.
Two-samp T-interval?
Yes, the two-samp t-int. That is the calculator shortcut for that. And all of these, if I'm not mistaken, you can either use with data that you have in your L1 and L2, or you can, if you have the statistics, it'll give you the choice for either one. So, in that testing, stats, and then test, just about everything in there, there's a couple of exceptions, and we'll learn about most of them. We'll have gone through just about every one of those tests at one point or another. But there's intervals and there's tests. Significance test is, are you in the tails? Intervals is, here's where we think the interval is, right? Okay, so let's look at a problem. 13.1 is on page 785. And they ask a question, Toyota or Nissan? can't pass up doing a problem that deals with cars. It just can't happen for me. So this question says, are Toyota or Nissan owners more satisfied with their vehicles? Let's design a study to find out. We'll select a random sample of 400 Toyota owners and a separate random sample of 400 Nissan owners. All right, so I'm going to write that down. Instead of N1 and N2, I'm going to call this NT for Toyota and NN for Nissan. They've questioned 400 each. Then we'll ask each individual in the sample, would you say that you're generally satisfied with your Toyota or Nissan vehicle? So A asks, is this a problem about comparing means or comparing proportions? Are we comparing means or proportions here? Are you satisfied or are you not satisfied? Is that going to give us, yeah, that's going to be proportions, right? Yeah. Some number out of 400 Toyota owners are satisfied with their vehicle, and some number out of the Nissan vehicles are going to be satisfied. So this is proportions. Which we haven't learned how to deal with yet. So I'm going to say this is going to be comparing satisfied Toyota over all of the Toyota and satisfied Nissan over all the Nissan owners. B. B asks a question that goes back a little ways. What type of study design is being used to produce the data? What's that? Single blind? That has more to do with, yeah, no, it wouldn't. So if it's an experiment, then the study, person who runs the study, I'm totally blanking the term here, but the person who runs the study is going to be assigning treatment. So in this case, the way I would see that is, okay, you drive Toyota, here's your Toyota. I'm giving you a new Toyota. You're driving a Nissan. I'm assigning you a Nissan car to drive. And I assign randomly Nissans and Toyotas to 800 people, right? Is that what's going on here? So is this an experiment? No, there's no treatment being imposed. So that makes it, what's that? It's not, well, it's observational. Yeah, observational study or observational survey. Observation being the key here. It's observational. It would be rather cost prohibitive to supply 800 people with cars. So it really wouldn't work as an experiment. Let me ask you this though. If you could assign people brands of cars, do you think that would make this more or less, I mean, is there any bias, do you think, to asking people who've already chosen Toyotas if they like the Toyota or not, or vice versa with Nissan? Yeah, you really can't get outside of the bias that would naturally exist here in most cases. Okay, so that's it for 13.1. Let's look at 13.4. It's a real quick one. Then I'll give you some direction for 13.5. 13.4 is testing chemicals. story here goes, the following situations require inference about a mean or means. Identify identify each as involving a single sample, paired data, or two independent samples, and justify your choice. So A says to check a new method of measuring the concentration of a chemical solution. A chemist obtains a solution of known concentration from the National Institute of Standards and Technology. She pours the solution in equal amounts into 20 beakers and then measures the concentration of the solution in each beaker with the new method. She checks for bias by comparing the mean result of her 20 means with the known concentration of the solution. So A, she's getting a known concentration, she's pouring it into 20 beakers, and then she's testing each of the beakers and comparing her test results to the known concentration. Is that a single sample, paired sample, or two sample? Unsure? You think single sample? I agree. She's just testing a single sample over and over again. Right. It's a single sample. Is she testing really the sample, or is she testing the testing method itself? I would say she's testing the testing method because she already knows what the sample concentration is. She's not comparing different means. B. Scientist number 2. Another chemist is checking the same new method of measuring concentration. He has no reference solution, but a familiar technique for measuring concentration is available. He wants to know if the new and old methods agree. He takes a solution of unknown concentration and pours it into equal amounts into 20 beakers. Then he measures the concentration in 10 of the beakers with the new method and the other 10 with the old method. Is that single, paired, or two independent? How so? You're saying paired, Jackson. How so?
I don't know. It's using the same population of solution, but doing two different treatments, I guess.
Yeah, he's testing the old method versus the new method. Paired would be like, think of twins. If you take two people that are purposely similar, and then you give one treatment and one the other treatment, that's a paired situation. I think he's looking at two sample here. He's split 10 of one and 10 of the other, and it should be all the solutions should test the same for all 20, but he's testing with two different methods. I don't think he's necessary, because he's not testing the same vial with both methods. He's testing the same solution, but he's literally using a different vial for each test. So this would be a two independent testing method, or where two independent means and he's testing the method. New versus old. He wants to see if the new method matches the old method. Okay, that's enough for me chatting about this. Let me give you some direction though here. With number 5, you'll have to read through this, but they give us two sets of data. And when we're doing this paired data, we don't have to have the same n values. They don't have to both have the same amount. And this clearly doesn't have the same n values. So what I would do is I'd put this treatment into like L1 and the control into L2, and then let the calculator do the work. You know, whatever it is that it's asking us here, see if you can't make those shortcuts in the test stats and then test work for you. Make sure you check your conditions though, and if you're doing a significance test, you want to set alpha. Okay, where do you think alpha should go? All right, I will let you go with that.